Good morrow, everyone. Today is lab 5, the Faraday to do it. Get it? Puns? Because today we'll be talking about Faraday's law. And despite the name, this will not take 24 hours. Faraday. Puns. Anyways, let's go ahead and get to an introduction for a description of lab and fundamentals. We'll then go into the data and observations for lab results and a Glowscript bit, and some final questions at the end. Now, some end goals for our introduction is to go ahead and try to understand Faraday's law just a little bit better through a failing magnet and an aluminum cylinder. It'll be kind of like the graphic that you see on the right now, where we have the force of gravity pulling some kind of magnetic dipole coming through downwards, and it's going to get some kind of induced kind of force that makes it go up a bit, while having the F-net still pull it down throughout the entire time. Some principles we'll be discussing is Faraday's law, Biot's-Savart, and Newton's lovely second and third laws. For some data, we'll have 1.25 seconds for real, and the model is 1.21 seconds. For the setup, I'm just going to go and skip through most of this, since, well, I'm assuming that we don't want to hear my lovely voice go through every single list item. The only thing that I do want to mention, though, is that mu 3.21 is previously derived from lab 3. If you guys would like to see the full derivations on that, along with some of the future formulas that we use to derive the rest of this video, please go check out the link in the description. So for some general notes before we get into some simulations. Why can't we use a ferrous tube? Ferrous tube contains iron, which would be induced from the magnetic fields and induce a current. This would interfere our data if we were to do, say, copper instead. Another question, what if it was dropped in free space rather than the tube? Magnets experiences a lens law to flow throughout the aluminum tube. So without the aluminum tube, I would say that free space is probably going to be faster. Now it's time for the Glowscript. Let's go. And we are back into the lab. So I'm going to run through the code really fast, and hopefully when you see it, it'll make a little bit more sense than my jumbled words. Initialize constants. Plot graph. First part, initialize as values we talked about earlier in the slides. Go ahead, make some time step derivatives to go ahead and try to calculate your simulation as it goes along. Luckily, I didn't have to make this. The kind people at the lab did it for me. Now, declare your other variables, mu mag from just lab 3 by the way. Visualize a power magnet. Go ahead and get your initial conditions and set them to equilibrium. Dipole of B, same formula that we used in lab 3. This part, calculate time derivative of flux for our calculations of induced beams. Now go ahead and just let it run downwards. From there, go ahead and declare force of gravity. Declare that mag of F on magnet is 0 for now. And for ring and tube, I want you to go ahead and get the d flux and calculate d flux time derivative flux pretty much by ring. And from there, just go ahead and calculate the current in the ring. Color the rings. Don't worry, this one wasn't made by me either. Pretty nice. Calculate the next 4 lines for kind of just what would you expect force to be on a ring, or be at ring more specifically. And just a bit of super duper bits of mag commands. Over here, go ahead and declare magnetic force on the magnet. Declare the net force on the magnet, and use your updates from Newton's second law for momentum update principles. From there, post it to your curve and just tell me when you're done. 3, 2, 1, let's go. So as it falls down, we could kind of see that the graph looks like this. Recall that from Newton's second and third law and all of his pretty beams, Popol, you can kind of see that when velocity is going to stay the same, that means that there's no acceleration. So that means that throughout the duration of the tube, somewhere between here and here-ish, you're going to expect there to be a net force that is equal to 0 when these two forces balance out exactly. Here and here at the end, these are not going to be the case. I'm going to leave it up to as an exercise for the reader to guess why, but you could kind of intuitively guess why already, just by thinking about it in real life. To help you answer this question, imagine that you get a friction full piece of sandpaper, you roll it up and you put a baseball through it. What do you expect it to look like? Alright, let's go on. Final questions. What if the resistivity of the conductor was to 0? How would that change the dynamics? Ohm's law says V equal IR, so IV divided by R is also true. So given that R is 0, that means that V, well, has to be pretty big. And so does I, if not even bigger. So time to fall through the tube would be infinitely long, if not impossibly long. What if holes or slots were cut into the tube? How would this affect your currents? Well, you could say intuitively that maybe the rings would decrease, or intuitively there might be less of something. There's going to be less kind of distributed area for your formulae that you derived. So, although I can't say for certain, I would probably expect a decrease in induced currents, which would then cause decrease in magnetic field, reduces time for the magnet to fall,